Electroplating is a plating process in which metal ions in a solution are moved by an electric field to coat an electrode. Electroplating is also called electrodeposition, a process for producing a dense, uniform, unreactive metal layer or plastic layer onto a reactive metal. The purpose of doing this is to prevent corrosion and rusting from happening, as we know that exposure of a reactive metal like aluminum and iron would lead to corrosion and rusting. Therefore, a layer of unreactive metal or plastic can prevent this from happening. There are three connections related to electroplating, including redox reaction, reaction surface area, and Faraday's law. The redox reaction drives electroplating to take place. First, we have to put the metal we wanted to coat on the cathode and the coating metal ion into electrolytes. Because of the insertion of battery, electrons are provided to the cathode and attract the anions around the cathode to reduce. According to the reduction potential table in appendix, an ion with a more positive E potential would be more readily to reduce. Therefore, it is suggested only molten metal ions or concentrated aqueous solution is used in order to ensure only metal ions are reduced. As shown in the picture, in order to have a continuous supply of coating ions available in electrolytes, the coating metal, copper, would be used as an anode so that it would oxidize and release the metal ions into the electrolytes until all are dissolved. In the electroplating setup, we can tell the cathode is reducing the copper ions and the anode is oxidizing the copper metal for continuous supply of metal ions. The next connection, reaction surface area. The rates of reaction are varies due to the concentration of the electrolytes, temperature, as well as reaction surface area. Especially the size of reaction surface, there is an observable change in the rates of reaction according to the reaction surface area of the cathode. The graph indicates that the cathode with larger surface area would react more rapidly as it has the steepest slope. A larger surface area of the cathode can enhance the electron to rush to the surface and facilitate reduction to take place. Besides, it can also let a larger amount of copper oxidize into the ions by having a longer and narrower anode instead of a square one. As shown on the right-hand side, the longer the electrode, the larger the surface area. The more the electron can approach to the nearest surface of the electrode, so that more metal ion can get to the contact or accept the electron and reduce from the metal ion to metals. The next connection, Faraday's laws. The amount of electricity flow is directly proportional to the amount of substance produced or consumed. That means the amount of copper dissolves into the electrolytes should equal to the amount of metal deposited on the cathode. However, this amount should be at a constant ratio to the electricity flow. Faraday's first law of electrolysis. The mass of a substance altered at an electrode during electrolysis is directly proportional to the quantity of electricity transferred at the electrode. That means the copper that formed on the cathode is directly proportional to the electricity flow of the electroplating system. Faraday's second law of electrolysis. For a given quantity of electricity, the mass of an elemental material altered at an electrode is directly proportional to the element's equivalent weight. Here depicted the equation from the Faraday's law. The first equation, Q, equal currents 10 times show that the mass deposit on the cathode is actually equals to how long the current flowed in the electroplating system. The second equation means that the mass of the copper dissolves is actually equals to the amount of electricity flow through the electroplating system.